Okay, before we start this video, I'll just make it clear that this is really beyond the confines of the A-level specification, but it's not that difficult to understand, and it's quite interesting, quite important. So that's why I'm going to talk about it now. Okay, so this is the titration curve for ethanoic acid, which has got a pKa of about 4.6, and the one on the right is carbonic acid. It's a much weaker weak acid, a pKa of 6.4. Now, if you remember, you can find the pKa by you get the equivalence point. Okay, from that you find out the half equivalence point, and then you extend that up onto the y-axis, and that will give you the pKa. So the pKa of ethanoic acid, yeah, is about 4.6 there. Okay, now if we remember when we're talking about buffer solution, you need plenty of HA. I'll just change the color here. You need plenty of HA, and you need plenty of A minus. And it is in this region here where you've got plenty of both. But when you get past the equivalence point, then you have it's all A minus. So that's no good, it won't buffer. And if you write down here, it's all going to be all HA. So the solution can buffer in that yellow bit that I've just highlighted there. And if you think about it, what's going to happen is you add a bit of alkali to it. The pH is gradually going to sneak up on that line, but not too much. And if you add a bit of acid, it's going to go backwards. The pH will sneak down a little bit, but it won't change too much. It's only if you got to about here, you got to this point, then you add 1 drop of alkali, the pH is going to rocket really high and make it very alkaline, and it's not buffering. So you can see that the ethanoic acid can buffer, and most people always say that it's plus or minus 1 unit either side of the pKa value. So it can buffer from that's about pH of about 5.6 down to pH of about 3.6 down there. So it's buffering okay in this yellow region here. You go outside of that yellow region, the pH too high or too low, it won't buffer. Now, you can see for carbonic acid then that's going to be buffering in this region here. So plus or minus 1 pKa unit either side of the pKa. So carbonic is going to be able to do it from 5.4 up to pH 7.4. It's going to be pretty good at buffering. Whereas ethanoic, it's going to be 3.6 to 5.6. That's where the pH range that can do. So you can see from that ethanoic acid would be no good if you want to have a buffer of pH 7. It's no good. You can't use it. And why did I say 7? Well, a lot of living things, you want it to be buffered at pH 7. So carbonic acid is this carbonic acid and its conjugate base, the hydrogen carbonate ion. That system is pretty good at buffering around pH 7. That's good. And this is if you're growing cells in culture, that is usually the way it's buffered. So the cells are, you have bicarbonate, hydrogen carbonate in the cell medium, and to make sure you have some H2CO3, you grow them in the incubator with a high CO2 content, like 5%, 10% CO2. And this is actually the buffering system that your blood uses. So your blood is buffered. It's usually about pH 7.2 or something like that, and it's buffered by dissolved carbon dioxide effectively, so hydrogen, carbonic acid, and hydrogen carbonate. Right, let's just go and do a little bit of maths on how that works out then. So if we get our pH equation, we've said that H plus conc is equal to Ka HA over A minus. Now, for a buffer to be good, you need lots of HA, and you need lots of A minus. It's no good having too much with either one or the other. So that means the value of this fraction, HA over A minus, and I've said this before in previous videos, it can be a minimum of 0.1 value and a maximum of 10. So in other words, you can never have more than 10 times more of the HA than the A minus, and vice versa, because you need to have lots of both of them. Yeah. Okay, so we're saying there that is for an effective buffer, for an effective buffer, the fraction's got to be in that range. Okay, so let's do the minimum. Let's have a look at this, and we'll do the minimum value of the fraction, and that's equal to 0.1. So in that case, we get H plus is equal to Ka multiplied by 0.1. Let's take negative logs of both sides of the equation. Well, if you do that, you get minus log H plus is equal to minus log Ka, and that times becomes a plus. Remember your log rules. Plus, sorry, it's going to be, because it's a minus log 0.1. Right, let's do a bit of substitution there. So we know that log H plus is pH, minus log H plus, sorry, minus log Ka is pKa. The log of 0.1 is minus 1, so that's pKa plus 1. Okay, so when you've got the minimum value, that's your pH value there. Right, let's do the maximum value on this side now. The max value of the HA over A minus is equal to 10. You've got 10 times more HA than A minus. So let's do that. You'll find there that you will get, so you get H plus is equal to Ka times 10. Do the same thing again. You'll get pH is equal to pKa minus 1. Okay. So that shows us that this is the minimum pH at which it will buffer for efficient buffering. And this is the maximum pH for effective buffering. Okay, and just to round it off, because we did say earlier, a buffer, an acid and its conjugate base can buffer in the range plus or minus 1 pH unit around the pKa value. So if you want an acid and its conjugate base system to be, to use at pH 7, you need to look for a weak acid with a pKa value of about 7. If you want to buffer down like pH 3, then you need to look for a weak acid with a pKa of about 3, and so on. As I say, you don't really need to know that at the A level, but I think it's quite interesting anyway. There it is all together.